Students create a robot parade. Making scientific glassware. Research to improve groundwater resources and working to perfect computer vision. But first, using wireless technology to fight wildfires in California. All on this edition of On Beyond.
People can be in harm's way very quickly. Decisions have to be made in a relatively short period of time. And that's where something like WiFire helps with managing those types of issues.
How about running a scenario on campus, just as you come off 5, and then running into the campus for 6 hours on a Santa Ana day?
WiFire is a lab of scientists at UC San Diego who have a goal of making data and modeling tools available for wildfire awareness and research.
So half an hour, 1 hour, 1.5, 2 hours, right?
The story begins in the year 2000 when the High Performance Wireless Research and Education Network began. It was founded by Hans Werner Braun and Frank Vernon at the San Diego Supercomputer Center. But CalIT2, now known as the Qualcomm Institute, was also working with emergency response agencies on simulating different types of scenarios and integrating technology. So the director of CalIT2, Larry Smarr, and the chief data science officer at San Diego Supercomputer, Ilkay Altintash, put those pieces together. So how you can make the technology and the hardware and the simulation and data science integrated into a platform that can be seamlessly intuitive to firefighters and the public.
When you think about a location and time that the fire starts, there is a number of data that you can bring together. So that one point is critical because on a high wind day, that means this can take on in the next half hour, 6 hours to be a large-scale fire event. If you could bring together all the data, you can actually enable fast decision support using models, data science, fire science. So that's what WiFire achieved, is that integration of data, models, scalable platforms, technology, together with people's expertise.
Field resources initially are very limited. We'll run a model, the initial model, here from the center, and with the capability of the program, we can put it in a shared file. I could take a picture of the screen, whatever means possible to be able to get it to those initial decision makers that are out in the field, because they're making decisions on what's a realistic containment area for this fire, if at all possible? Where are we going to be able to stop it? So then how do you begin to start to prioritize your structure protection? How do you begin to prioritize your evacuation needs? How do you begin to prioritize what communities you need to do alerts to and start letting people know at 1 or 2 in the morning that, hey, you got a fire in your area, we need you to wake up and start paying attention to some local media for some information.
We built the WiFire platform to be as intuitive as possible, so you can turn on weather stations and see which direction the wind is blowing and how hot it is. You can see the different vegetation types, and you can see where the city is. And you can also open up the web cameras from HPREN and Alert Wildfire and take a snapshot of those cameras and see what the weather looks like.
HPREN is a fixed wireless network that crosses San Diego County and provides to the public real-time weather and image information of the county around them. HPREN images are crucial to WiFire mapping because it gives WiFire users the ability not only to have a geographic overview of the fire perimeter, but to actually see the fire perimeter. The weather data is preferred weather data because the HPREN meteorological stations update every second, and they have access to that per second updated weather data.
So if the models aren't behaving properly because the input data isn't right, we can update that with the new information that we're getting from aircraft. A lot of the software systems used for fire simulation today require a lot of manual input. The way that WiFire works is automating a lot of that so that you don't have to coordinate and specify a bunch of data sets that are already there for you. That makes the system faster and can work for you.
Red, orange, pink, yellow is basically a prediction where the fire is going to go. The process we use to predict where the fire is going to go consists of a joint combination of prediction and estimation. And some of the estimation involves things that you cannot really directly observe. So a good example will be the burn rate of the fuel. How fast is it burning? Those factors are part of the model, but you don't know what they are, right? You cannot directly observe them. And so what we do is we take an observation and realize, wow, the fire burned much faster than anticipated. So we can then learn those adjustment factors so that next time our prediction is better.
People from all over California during the last couple of years, every single big fire, they come and find the system. And we have huge spikes in the usage of our system. For instance, in fall 2017, we had more than 8 million page hits by 800,000 people. And when you think about it, it's a huge number, 800,000 people. Who are these people? It comes to mind. But these are really the public, the people who have loved ones in the path of the fire, or they are in the path of the fire or in an evacuation center, and they're trying to understand what's going on.
WiFire system provides scalability. So when only a few people are running the model, it runs on just one machine. And as we get more people running the model, it scales up to various clusters here and elsewhere in the cloud.
California had more than 6,000 fires in 2018. And more than 99% of these fires were suppressed. So fire suppression is actually pretty good. What's changing is the conditions these fires happen. We have stronger winds, we have a big fuel buildup, which is the vegetation that burns. So when a fire happens now, we are seeing all kinds of new behavior. So these 40, 50, or sometimes even a handful of the biggest fire evers, or this fire is uncontrollables, or we don't understand this behavior, or we've never seen this behavior before type of fires are happening because there's something new going on. And you can't model those fires with the understanding that you bring about previous or past fires. So we need to understand these fires while they're happening so we can actually adjust the models. We live in what we call wildland-urban interface. That's where we built our houses. And some of those wildland areas actually need fire to renew. So for the health of that ecosystem that we build our houses on, might need that fire to be burning. So over time, with proper management and proper understanding of fire behavior, we can probably manage these fires differently. That will be much healthier for our ecosystems and our communities as well.
My name is Steve Swanson. I'm a professor in the Computer Science and Engineering Department. And this is CSE 91, a class I call Robot Parade, or Designing and Building Robots. And it's a class for brand new freshmen. So these are all in their first quarter. All the students here are in their first quarter at UCSD. And the idea is to get them into the Maker Studio and get some hands-on experience building things and programming things in the real world. And the way the class works is for the first 4 weeks, we have them work with robots that we built for them, like this. And they have different features. This is an LED array. There's a little speaker to make noise, and it can drive around. So they learn how to drive the robots around, how to program them, and kind of the basics of getting around the Maker Studio. And then For the next 2 weeks, we have a different robot that has some sensors, distance sensors, and has a gripper and some other things. And then after they've learned to use those robots for 4 weeks, then they get to design their own robot using some software that my lab has developed that makes it really easy for people without a lot of electronics experience to build things like simple robots. So we manufacture them, and then today we're assembling them, and they're going to program them for the next 2 weeks in the quarter. And then we'll have a big party at the end where they all drive around and interact and run amok. I don't think there's going to be too much destruction, but I guess we'll see. We've never had quite this many robots. So at for the final robot parade, we'll have about probably 40 of the robots that they've built, and we'll throw some of these pre-built robots in there too, so maybe 50 or 60 robots altogether. We'll see what happens. We've built this class so that it's specifically supposed to be accessible to anyone. So you need no skills at all. We teach it in parallel with CSE 11, so they're learning to program in that class, and then we've sort of matched the programming that we do in here to line up with what they're learning in that class, so they can come in with nothing and come out with a working robot. The Maker Studio is part of this JSO initiative for getting freshmen in to do things hands-on very early, and so this is the computer science class that is part of that effort. So we have the 3D printers, we have the laser cutter, we have the foam cutters, and so one week of this class we talk about 3D printing, and they design something to be 3D printed, and people have built some pretty creative things that they're going to attach to their robots to kind of give them a little extra personality.
This is supposed to be a territorial seal. If you guys heard about Gerald, like from Finding Dory, he's a seal. He's got like wonky eyes, and he's always bullied and like chased off the rock. And you know how seals like their own rock? So this is like the revenge of Gerald. So he kind of took up like the center 15 centimeter radius area for most of the time it was running. So it basically just goes in a circle looking for things that's closer than 15 centimeters and then chases them and pushes them away. Okay, so Gerald has a distance sensor in the front, and this allows it to see, it senses distance in front of it. So whenever something is less than 15 centimeters in front of it, it'll chase it, and then it'll like run into it, and once it becomes 0 centimeters, it'll think that it has pushed it away far enough, and then it'll back up and continue its search in a circle.
They seem to like it really well, especially at the end when the robots are all there driving around, interacting with one another. It's pretty exciting. I've had really good response from students that have taken the class, that have come back and have been tutors for the class. They've been very enthusiastic about it.
For a lot of the students, it was completely brand new to them. Putting together their robots and programming them, at least the first time when I did it, I could say it was definitely a cool experience, and I could definitely see some of the students sharing that sentiment as well. A lot of what we try to teach in this class is just ways to think about programming, and I would say that some of the skills learned in this class can definitely be taken forward using finite state machines, programming their robots using C++ and Arduino. Giving them early exposure to that will prepare them for things that they might see in the future. Trying to find the best way to express what you want the robot to do and to have it actually do it is a really satisfying feeling to see being done.
So the idea is to get them hands-on experience really early so that they know that they can build something. A lot of these students have never soldered before, maybe they've never built anything before. Maybe all the programming they've done has been just in the computer. But here we're programming things in the real world. That raises some interesting programming problems. And it also is very kind of instant gratification of seeing something that you've built drive around and interact with things in the real world. So the hope is to get them excited, hopefully get them to stay in computer science, learn more about computer science, and do well in the major.
There's a time when you are essentially in the zone with the glass. It has all your attention. It's almost like a meditative practice. If you're distracted for a second, the whole thing can collapse. and you start over. I like being in that zone. My name is Jim Breen. I've been at Berkeley 16 years. I make custom glass apparatus for the researchers to use for their experiments. I don't make off-the-shelf test tubes and beakers and pedestrian glassware. My time is better spent making complex apparatus. I probably make about 500 pieces a year. I started working with glass in high school doing stained glass windows. And that's pretty much all I needed. And I decided that I would find a way to do it for a living. Some of my ancestors from my dad's side of the family back in the 1800s were glassblowers. So I guess it's in our DNA. Everybody at UC Berkeley wants the impossible. It's either something that's too small or too big. I never say no. I always figure out a way to make what the researcher needs to have. And it's up to me to extract out of their imagination something that I can make. A lot of the research groups here are doing environmental research.
Our lab is interested in reconstructing how temperatures varied through time.
We're taking molecules from trees to understand the climate in which the trees were growing in the past. Reconstructing climates in the past, which helps us understand what climate will look like going forward.
When I arrived at Berkeley, one of the first things I did is go and meet with Jim. I knew that I had to have a vacuum line designed and built and made custom. You can't get these things off the shelf.
Daniel and Jim have put together a lab that is so good and so flexible for doing exactly what we need to be doing.
You rely on having people who support the work being done here that are true experts in their trade and in their craft. And they are critical to allowing us not only to do what we want to do, but helping us get there.
It's very gratifying that I'm able to help them along the path that they're on. The kids these days, well, they're going to save the world. In a small way, I'm making a contribution.
Rainfall is never a promise in California. In drought years, California borrows water from its underground aquifers, pumping groundwater to make up for the shortfall in surface water. In other areas of California, like in the Pajaro Valley on the Central Coast, the freshwater supply comes from groundwater every year. If more water is pumped out than is replenished, groundwater supplies shrink. Andrew Fisher is a hydrogeologist at UC Santa Cruz studying groundwater recharge in the Pajaro Valley. His lab is working on a multi-pronged effort to not only increase supply, but improve water quality and come up with ways that encourage water users to take part.
The Pajaro Valley is an interesting place to work, and it's also a really good place to work in studies of groundwater recharge because the region is very dependent on groundwater. It supplies about 85% of their freshwater needs. The valley is not well connected to the big water infrastructure for the state. The Pajaro Valley has to make do with the resources that they have. Because they grow very high-value crops, they have a lot of incentive to solve this problem and figure out how to manage their water more effectively.
So an aquifer is a layer of material underground that contains enough pore space between the grains of rock or sediment that it can store and transmit water. It's more like a sponge And we want to identify the places where a recharge project could be most effective, where we could get the most water in the ground and have the most benefit.
To answer that question and others, Beganskis is developing a regional hydrologic model.
Some of my lab mates have worked on making maps that incorporate data from the bedrock geology and the soils. How easily can water move from the surface down into an aquifer? Is there an aquifer even there? These are important considerations to think about. So my focus has really been on the supply side, and the supply that we're focusing on is excess hill slope runoff. So when it rains, and especially during very intense rainstorms, water will flow over the land surface, and we're interested in collecting that runoff during intense storms before it reaches a stream. I've been working at a stormwater collection field site for the last 6 years. 4 of those years included the severe drought in California. And in one of those 4 drought years, the project exceeded its goal in terms of how much runoff it collected. And so even a single intense storm during a dry year can create a lot of runoff and can create opportunity for improving groundwater supply.
It turns out it's usually a lot easier to clean water before it goes into the ground than it is to clean it after it's become groundwater. Our primary focus in improving water quality so far has been on nitrate.
Nitrate is one of the most pervasive contaminants across the United States and across the world, especially in agricultural areas. It has been linked to ecological damages, like harmful algal blooms. It's also been linked to human health problems.
We know that there are microbes that live in the soil that can naturally remove nitrate from water as that water is passing through the soil. And so our question was, how can we stimulate those microbes? How can we enhance their growing conditions, make them more likely to remove nitrate at a faster rate so that we can maximize the removal of contaminants from water as it's infiltrating into the ground?
The students in the Fisher lab ran multiple experiments at different scales, using soil cores in the lab, 1-meter plots in the field, and full-size infiltration basins to discover it's the wood chips.
In our experiment, we tried 2 different conditions. We tried one where we just had the regular native soil, and we tried another where we added a layer of redwood chips. The thinking being that adding a carbon source like wood chips can help stimulate that process.
The column that's amended with redwood chips removes the most nitrate across a range of infiltration rates.
That's an indication that doing something as simple as adding a layer of redwood chips or mixing the redwood chips into the soil can have a really big impact on the microbial community. And that in turn can have a really big impact on the water quality.
And while the science side is coming up with good ideas, Fisher is also developing a way to address the economic and social side of groundwater management.
We've been working on an idea called recharge net metering that we've adapted from something that public utilities have done for some years as a mechanism to encourage people to generate electricity. In the case of energy, it meant putting a solar panel on your roof, and then if you had excess energy that you weren't using, it would go out onto the grid, and your electrical meter would actually run backwards. In the case of groundwater, we can't make a groundwater meter run backwards, but if we can measure how much water goes into the ground because of certain activities, then someone could be issued a credit against their water fees in exchange for whatever those activities might be. And that revenue can then be used to maintain those systems so that they can continue to infiltrate more water into the ground over time. Because I think this is going to be a learning process as we see what works in the Pajaro Valley and then what might work in other parts of California.
My group and I, we work on computer vision, and computer vision really has a lot of applications around us. Computer vision is also a really interesting field of scientific inquiry, a beautiful marriage of math, physics, computer science, engineering, neuroscience, biology, and so on. There are lots of applications, and there are fundamental, interesting scientific questions to solve. 2 important problems that we look at in our group are reconstruction and recognition. The problem of reconstruction is, given images, we want to recover 3D information and shape properties about the world. Recognition is also a challenging problem because the information that is presented to the computer is just a bunch of pixels. How do we categorize these pixels into semantic information is a challenge, and the recognition problem looks at solving this challenge. We want to bring insights from our knowledge of the geometry and physics of image formation and use that to create better data-driven deep learning engines. These deep learning architectures have intrinsic abilities to be able to capture how the images that are present in the training set have been created. Some of the applications of our work are self-driving, where we want to reason about distances of various objects, or we want to reason about whether that object is a car or it's a bus, or whether that is a pedestrian. Is that pedestrian moving or is he static, waiting at a traffic light? A challenge is that we don't know how our current models are going to work in different conditions, which could be nighttime or which could be rainy weather. So by adopting some of the approaches that we are doing, we can allow these machine learning models to work better across all different types of conditions. Another example is where we work in challenging environments such as underwater images. So imagine that you are observing coral reefs under the surface of an ocean, which, by the way, is a very real problem that the Scripps Institute out here is working on. The approaches that we adopt is to generate training data to develop novel deep learning architectures that can be used to undistort images that have been obtained in challenging underwater conditions. We have a set of faculty here whose interests span across a spectrum of areas that computer vision is interested in. We also have Visual Computing Center, which is really a venue for academia and industry to interact with each other, and that provides a really fertile breeding ground for new ideas or truly collaborative interdisciplinary research. I think that's really what makes UCSD one of the fast rising new places for high impact computer vision research.